to this clay lecture today. This is a very special event because we are celebrating 25 years of the Clay Fellowship. I'm delighted to say that Thomas Clay is here, and I'm delighted to thank Thomas Clay and his family for the 25 years of support. So I'm going to give a brief introduction and then we're going to let Alice take it away. So I'm delighted here. It's my great honour to oversee this fabulous institution with an outstanding team of scientists, engineers, students and staff, and of course fellows. And our mission is to help understand the universe, our place in it, and to really address the biggest questions in the universe. And we're going to hear how Alice has been addressing some of the biggest questions that we have at the moment today. For 25 years, part of our mission has been achieved through the Clay Fellowship Program. And Landon and Lavinia Clay established the Clay Fellowship Program in 2000, and that was to encourage and celebrate the observatory's outstanding researchers displaying significant promise in theory, observation, instrumentation, and laboratory experiments. Today we had a wonderful lunch with some former Clay Fellows, as well as current Clay Fellows, and Thomas. And Thomas has been given a booklet which has wording from each of the 30 Clay Fellows over the past 25 years about how the Clay Fellowship Program has impacted them and their careers. And it was wonderful to hear from some of them today, and it's wonderful to see the real life impact of this fellowship program on young people, their careers, and also on the discoveries and where they went to beyond the Clay Fellowship. It's safe to say this is one of the most prestigious fellowship programs in the country as well as in the world. We heard from Clay Fellows today who had turned down other fellowships, including the Hubble Fellowship, to take up the Clay program. What makes it great is that it's a 4-year fellowship program, which means that the fellows can do a really ambitious research program, more ambitious than typically possible with fellowships. And it really allows them to focus their full time on their research rather than take up a position where they might be spending a significant amount of time doing teaching or other service work. So to date, the fellowship program, as I said, has supported more than 30 early career astronomers, and they've now become leaders in the field, and they're guiding the next generations of scientists. Landon Clay was a Harvard alumnus, and he was a Smithsonian National Board member, and he had a keen interest and dedication to scientific progress that led to numerous breakthrough discoveries in a variety of fields. One of his greatest contributions was the strong support of young scientists in a wide variety of areas, including astronomy and mathematics, and he had a great love of mathematics and how it applies to our understanding of the universe. Here today to celebrate Mr. Clay's legacy at SAO is Thomas, one of his sons, and he is the incoming chair of the SAO Advisory Board. It's been my great pleasure to work with Thomas over the last 3 years as a member of our advisory board, and I'm just delighted that he's going to be taking over the reins of the advisory board, and I'm really looking forward to working with him in the coming years. On behalf of the Smithsonian Astrophysical Observatory, I want to express my sincere gratitude to the Clay family for their 25 years of generosity, and that's made a significant impact on SAO and the fellows in the program. At this time, it's my pleasure to introduce Alice Booth, who's going to be delivering today's Clay Colloquium. And she's going to be talking about characterizing the chemical landscape of planet formation. And also Alice's family, father and uncle are here as well. So welcome, and I'm sure that we're going to hear exciting things today. So take it away, Alice. Great.
All right, so good afternoon, everyone. It's really great to be here to share some of the research I've been doing here for the past year and a half at the CFA. I'm particularly grateful that my family can be here, and grateful to have also Thomas Clay here as well. It's really a great privilege. So I'm going to talk about astrochemistry today, molecules in space, and how we can link them to the origins of planetary systems. So we want to orient ourselves first in the solar system. Here we are on Earth. It's very nice here. We can live here. I don't think we can live anywhere else so far. But there's a lot of variety in our solar system, right? We have a lot of other planets, moons, other smaller bodies. Particularly, we have these small, potentially habitable planets, and we have at larger distances these gas and ice giant planets, and we also have a lot of things like moons, asteroids, and comets. And this is a lot of variety, and a lot of our work is trying to understand where did this variety come from, how are the compositions of these bodies different, what determined all of these kind of layouts that we see here today. And when we look beyond to other stars beyond our sun, we're finding a lot of exoplanetary systems. So of the over 5,000 different exoplanets found around nearby stars, we see an even order of magnitude or more differences with our solar system, a lot of variety. And we want to try and understand how we can have such planets and where they come from and what determines what they're made of. So there's some big questions popping up in exoplanet science now, a lot of this fueled by observations with JWST, the new James Webb Space Telescope. And some of these are things like, what determines the bulk composition of a planet? So with JWST, we can measure the kind of elemental abundances in a giant planet's atmosphere, and we want to understand, how did it get that much carbon or oxygen or nitrogen? And maybe the more fun question to think about is if any of these smaller planets are potentially hospitable to life. We can live here on Earth, or are the conditions that created that ubiquitous in the galaxy or not? So I'm going to try and tackle these questions from the lens of astrochemistry. So we want to understand the chemistry within protoplanetary disks, the formation sites of exoplanetary systems. So we have to take a step back first before we talk about building planets. We have to talk about building stars. So this is a schematic of what we think happens in the low mass star formation process. So we start with a cold molecular cloud. By cold, it's tens of Kelvin, pretty dense gas. This is our time zero. At some point, gas in this cloud will collapse, and we're going to form what we call a protostar. This is a young star sitting, let me see, this is not working. We'll have a young star forming in about 10 to the 5 years. It'll start accreting material from the cloud. This inflowing material is going to rotate, and then we're going to form a circumstellar disk. After about 1 million years, we call these things class 2 planet-forming disks, and within these disks are where we're starting to build planets. And at some point, we might end up with something like our solar system or an exoplanetary system. And my work is really looking at what is happening at this intermediate stage, and in particular, what is the chemistry in this environment where planets are actively accreting their atmospheres. So this is a schematic of a disk, and we're going to build some planets in it from the dust up. So we have a young star here on the left, and then we have this disk where we have as a function of radius, so outwards in the disk in the plane, and then upwards as height. So we see this kind of flared structure. The temperature structure of the disk is mediated by radiation from the star. So we have hot gas here, it gets colder as we go further away, and similarly it gets hotter as we go further up. This disk is mostly gas. About 99% of the mass is gas, and most of it is molecular hydrogen, and that's something we have a lot of trouble observing directly. So most of the molecules I'm going to talk about are trace species, which are made up of carbon, oxygen, nitrogen, and sulfur, and they're less than about 1%. Within the disk, we also have dust. That's what's going to build up to form our cores of our planets, and this dust will start off at sub-micron sizes, so really, really small, and should over time grow to be centimeters or larger. And these dust grains are pretty great because they also provide a surface for molecules to freeze out when it gets cold. We have these, interstellar snowballs, and we have a lot of ice. And these can be simple ices, so water, or more complex things, as I'll talk about later. So this is kind of how we think our disk might start, and over time it's going to evolve both physically and chemically. So you'll see that eventually, we hope that the dust grows to larger sizes. It settles all towards the middle of the disk. And we're going to build planetary cores, hopefully. So that's getting us from a couple of centimeter-sized things to meters, kilometer-sized things, potentially. And where our planet's forming as a function of radius matters because we have ices in some regions and we don't have ices in other regions. So at some point in the disk, it gets cold enough that our water sticks on the surfaces of dust grains, and in some parts it's too warm and all the water is in the gas. And at some point, we hopefully build a giant planet, and that's going to have an appreciable impact on the structure of the disk as well. So we're going to build maybe little planets close to the star and giant planets a little bit further away. And these are going to create these big gaps in the physical structure of our disk. So we're going to have holes in the gas and the density structure that maybe are going to be observable to us with telescopes. And this giant planet's going to eat up material from the disk. It's going to feed from the disk gas to build up its atmosphere. So the material in the disk goes into the planet. So the chemistry going on here is really important for setting these atmospheric abundances. So we can think about what this might look like in real life. We have a baby Jupiter planet here. It's forming in a protoplanetary disk nearby. It's surrounded by this little disk or envelope of dusty material that it's accreting from. And then it's sitting kind of within a much larger structure than itself. So this is kind of coming into focus here is this big ring of dust. So these are actual observations of a nearby protoplanetary disk taken with the ALMA telescope. So this is on about 30 AU scales, and this is the PDS-70 system that is relatively nearby. So we have about a 5 million year old star here at the center. We have a young giant planet forming. This is a kind of image of a baby planet, which I think is really cool. And maybe it's forming little moons around it. The amount of dust here is about 3 lunar masses of dust. So that's very, very small. And we can measure that from, Earth. And then what's more appreciable or has a bigger impact is this really giant ring of cold dust that's kind of trapped in the outer disk due to the orbits of this planet. And this is mostly what we observe. This will be thermal emission of 20, 30, and 40 Kelvin dust. And that's what we can see with our telescopes, that kind of telling us that maybe we have planets hidden in a lot of these systems. So we want to know what the chemical environment of a young system like this is and try and figure out what material it can feed from. And this is kind of what I focus on. So we care about molecules and disks for a lot of reasons. I'm going to show you a table in a bit with a lot of different molecules, and it's not just stamp collecting. They tell us a lot about physics and chemistry. We can learn about the mass of the material, so do we have enough material to build a planet? We can learn about the temperature structure, and we can learn about magnetic fields, ionization. I won't talk about magnetic fields at all, so no one needs to worry. But they all give us a little bit of a piece of the puzzle, right? So we like to look at simple molecules. They're going to carry the bulk of our elemental reservoirs, so things like carbon, nitrogen, and oxygen, and that's what we're going to link to giant planets. And then if we look for maybe big game hunting, we want to find big molecules and disks, right? And that links us to the potential for prebiotic chemistry and trying to understand kind of origins of life through this lens. So we found about 30 molecules and disks so far, which is quite a lot. Not as many as if you look to other regions in the interstellar medium, but we've got a lot to play with now. These are ordered in terms of the number of atoms, so it's mostly small, simple molecules, but we're starting to creep up to larger things. The colors here show different elements, so we've got everything with, a lot of things with oxygen, carbon, nitrogen, and sulfur. Nothing with phosphorus yet. We're still missing that piece in our puzzle. And we also have isotopes too. Isotopes are nice tracers of kind of the thermal history of molecules or the radiation history of things, so we can look for heavy hydrogen, deuterium, 13 carbon, oxygen isotopes, nitrogen, and sulfur. We've picked up kind of all of the kind of isotopes in at least one molecule now, which is pretty cool. And this is all done over a range of facilities. Everything that is in bold was found at sub-millimeter wavelengths for the first time. So that is things like the IRM 30-meter telescope, NOEMA, the SMA, run here through SAO. And then everything underlined is found with ALMA for the first time. And what I'm going to talk about today are these kind of simple sulfur molecules and these larger ones. And these big molecules we've only been able to see due to kind of the unique sensitivity of ALMA, and this is kind of pushing the envelope into chemical complexity in disks. Right, so this is ALMA. ALMA's in the desert in Chile, but this is a picture of it in the snow, because I think it's quite neat. And the problem we have in astronomy is when we want to make higher resolution images, we need bigger telescopes, but it comes to a point where we can't build a telescope that is 10 kilometers in size. That doesn't really work. So what we do is this thing called aperture synthesis, so we have a lot of smaller telescopes laid out over the desert or the snow, and we kind of interpolate the signals between all these telescopes to pretend we had a really big one, and that works pretty well. It's a close-up of the antenna. They're about 12 meters in diameter, so they're pretty big. These are some people, and this is in the north of Chile. So it's really great to use this telescope. It's kind of an international facility, and it gives us kind of the best view we've had on protoplanetary disks to date. So disks have a lot of molecules in them. They're chemically rich. On the left here, we have the millimeter dust. So this is the thermal emission from small dust grains. And we see rings. Maybe we have forming planets. And on the right, this is a kind of gallery of different molecules. There's a lot in this plot. And you see that some molecules have small distributions. Some have larger distributions. Some have very clear rings. Some are a bit more fluffy. But the takeaway here is that pretty much all of these molecules are carbon-based. We have a very rich carbon-based chemistry in the atmospheres of disks. So the in-situ chemistry happening in the disk is very, very rich in carbon. I'm emphasizing carbon because it's not oxygen. We have a lot of carbon in the disk gas, but relatively little oxygen. So that means if we're building planets in these disks, they're going to create a lot of carbon, and we want to think if that makes sense. So from a kind of disk chemistry 101 point of view, it does. I mean, this is our physical structure of our disk. In the inner regions where it's warm, everything on the ice is in the gas, and we have a lot of water. Within this region, we have a lot of water, complex organics, simple oxygen-bearing sulfur molecules, and we have a low abundance of carbon relative to oxygen. So we have oxygen-rich gas. As we go out into the disk on tens of AU scales that we're probing with ALMA, we have a carbon-rich gas that kind of appears. We have less oxygen in the gas, so carbon is dominating, and we have these simple molecules like CS, C2H, CN, and we have this carbon chemistry. So this is great. We kind of understand what's happening in the disks, but how does that compare to evolved or new exoplanet systems? So these are 3 directly imaged exoplanet systems around nearby young stars. They may be about 50 to 100 million years old. So they're some of the youngest planets that we know of. And they're orbiting in these things called debris disks, so they have a little bit of dust left. And you can see these little points are all directly imaged planets. And we have a pretty good idea on potentially the atmospheric constraints of these planets, so what these atmospheres are made of. And overwhelmingly, they're oxygen-rich. So these wide orbit exoplanets have oxygen-rich atmospheres, and that's kind of the opposite of what I told you about the disk. So that becomes a little bit of a problem. We have to try and understand how to put these 2 pieces of information together. So that's only a few disks. What I've been working on really is trying to survey larger numbers of disks. And this is kind of my family gallery of disks I've been working on for the past couple years. They all have lovely phone numbers. And this is the dust emission. So this is the thermal emission from the small dust grains. This disk has a nice ring. This is an asymmetry where the star is here. Dust is all sitting on this side. A couple of rings, some more rings, maybe some spirals. And exactly how these structures occur, we're not sure, but they are potential signposts of planet disk interactions or interactions with smaller binary stars. So we have a lot of things going on in these disks. They're probably the sites of the formation of planets, so that makes it kind of exciting to study them. So what we've been doing is surveying with a couple different ALMA programs to try and figure out what is the gas content in these disks. So in particular, what we've done is look for simple sulfur-bearing molecules, so SO and CS, because they can tell us a little bit about the relative amounts of carbon and oxygen in the gas. And we've been building up a pretty nice inventory, and we found a lot of cool stuff. So this is maps of the SO gas, so sulfur monoxide, simple sulfur molecule. They all look a little bit similar. This one's a little different, but don't worry about it. It's here. And we see that we have these bright blobs. I would love prettier pictures, but one day. We have these kind of bright blobs of emission coming from about the same scale as we have these dust disks. So this is oxygen-rich gas in the disk on tens of AU scales, and that fits relatively nicely with the picture of these exoplanetary systems. So if we switch to our more carbon-rich molecule, CS, you see it looks different, right? If I go back, these molecules are not doing the same thing. In particular, if we look in this one in the middle, we have this centrally kind of peaked component of SO. We step out to the CS, it's this big donut with a hole in the middle. So we can use this information to see that we must have radial variations in abundances of carbon and oxygen in the disk, where we have oxygen-rich gas closer to the star and carbon-rich gas further away. So that's pretty cool. So now we want to put this in a proper context, right? We want to look at a system where maybe we have a planet and try and trace the accretion reservoir of a newborn planet, because that's more fun, I think. So this is a map of the thermal emission of dust from a nearby system. It has this really big gap out here at about 40 AU. And it would be really fun to just put a planet in the gap, because that would make sense, and that would be a nice kind of thought experiment. It doesn't need to be a thought experiment, because there is evidence for a potential protoplanet in the system. So these are 3 images, kind of in a GIF, of scattered light observations, where you see this little point source within the gap kind of moving on timescales of a few years. And this is consistent with Kepler in orbit of a few Jupiter mass planet sitting at about 40 AU. So this is pretty neat. This may be one of the youngest planets that we've detected to date. So what I did with some colleagues is try and pull together all the ALMA data we had on this system to try and build up a picture of what material this planet could be accreting in the disk. So we'll start here with our dust disk, and we have these 2 rings. We have the planet here, orbiting this way. We've got another gap, so let's just think we have a planet here and see what it could be made of as well, because that makes it double fun. So first we start with our carbon-rich molecule, and this is our CS. You can see this kind of big ring structure sitting with this outer planet. So it seems like this planet is in a region where the disk gas is more carbon-rich than oxygen-rich. If we add on our sulfur-rich molecule, or the oxygen sulfur-rich molecule, you see it sitting in a different place. It's near this potential other planet. We have no constraints on where in azimuth this planet would be, but it's just sitting there for aesthetics. But you can see that this oxygen-rich gas is, outside the orbit of this planet here. So we have differences. So we can try and piece together what we might expect. So from this simple picture, we probably expect, if we have multiple planets in a system, that they would have radial abundance gradients. So the planets closer to the star would have more oxygen. As you step further away, they become more relatively carbon-rich. So our planet in the outer disk, sitting with the CS gas, it can accrete probably, slightly more carbon-rich gas than the planet in the inner disk. which is within the water snowline, getting a lot of oxygen in the gas and potentially a lot of sulfur as well. So this would be kind of a neat story where things would just make sense, just from this kind of simple suggestion. But we found a lot of other things in this disk, and one molecule that we found for the first time was a silicate molecule. And silicates, they should be within the refractory material of the dust, so they shouldn't really be in the gas. They should be actual components of the dust. So to get silicates into the gas phase, you need some energy. You need a shock or something to kind of disturb these dust grain mantles and get the silicon into the volatile phase. And we found this arc of SIS here. So this is silicon sulfur, and it's this arc sitting within the gap of the disk, kind of located loosely where the planet is. And it has a weird kinematic signature as well. So we thought about this for a little bit, and it could be a few things. It could be shocks driven by the planet-driven outflow, these kind of spiral density waves the planets will induce as they're forming in the disk, shocking maybe this region of the disk. But all in all, we shouldn't see this molecule in the first place, but we do see it. So it's telling us something interesting is happening that we didn't really think about before. And if you have a bit of a key now, you see there's like a pink blob next to this planet as well from the SO. And SO is also a shock tracer in astrochemical environments. So this is something that's going on around this planet that we maybe didn't expect. And we've seen a few of these kind of asymmetries in molecular line emission in disks where we think we have forming planets. I've talked through this one on the right. This one on the left, I like because it's pretty clear. We have our star here and we have this very bright emission, and it's, a factor of 3 or so less bright on the other side. And it could be nice to think that maybe this is due to a planet. This data is pretty fun because I looked at this system as the first paper of my PhD. 2018, we published this gray spectra here. We got follow-up about 8 years later. I was pretty excited to finally get a chance to look at it again. We got much higher resolution data and found this kind of asymmetry. But what we see is that the kinematics of the line shifted a little bit over 8 years. So maybe we have some time variability. An 8-year baseline is about a quarter of an orbital period for a planet in the system if it is located here. So maybe we're seeing, changes in chemistry as a function of time due to planet formation, which could be pretty neat. I think this is something we need to start exploring now with ALMA. Now we have initial data sets and a lot of objects. We need to go back and see if things change, on 5 to 10 year timescales, because that would be pretty fun. So maybe we have a planet here. I would like that a lot. We've not figured it out yet. But that means our planets are doing something to the disk, right? They're not just accreting material from the disk. They're having an impact on their environment. So that means that our planet's not just sitting in the disk. It's like doing stuff. It's heating up the environment, maybe inducing shocks. And those are all going to change the chemistry that's happening. So our planet here might not be as quiescent as we thought it would. And what that does is it means that we actually might have a lot of oxygen in the gas at distances where we didn't expect it. So these planets are able to accrete oxygen-rich gas beyond the water snow line, and that also ties into what we're seeing in exoplanet systems. And this might only be applicable for the most massive, giant planets, but those are also the ones that we can readily observe. So that makes it good, and we need to start thinking about this. So yeah, the feedback planet formation has on the disk chemistry and how that affects planet composition is something that we need to start exploring. Right, so I've talked a bit about what determines atmospheric compositions of planets. I'll say there's a path to do it. Involves a lot of data and a lot of modeling, but I think there's a way that we can start to link these fields together better. So this was question 1. Part 2 is thinking a little bit more outside a little bit more exciting, or if any of these planets, could be habitable or hospitable to life. And that makes us think about what habitability means, which is a very big conversation. But in the simplest terms, when we think about life on Earth, what we need is a solvent, so water, which we need. We need energy, we have the sun. And we need to make sure we have all of the kind of elements that are essential, bioessential elements. So this would be carbon, oxygen, nitrogen, phosphorus, and sulfur. If we have all of this, we can kickstart prebiotic chemistry. Great. So what do we think about if we have a planet that's just the right distance from the star, that we have liquid water, the radiation field from the star is friendly enough that it isn't going to sunburn us all and we'll die, then maybe we want to think, maybe we can kickstart this process if we have the delivery of material from other solar system bodies. So that would be namely like cometary impacts or delivery from asteroids or meteorites. So this is the surface of a comet. This is 67P, which is a solar system comet that was visited by a spacecraft. So this is the video from the surface of a comet, which I think is really nice. You can see there's a lot going on. These are rocks, boulders. It's snowing on a comet, right? That's pretty cool. And actually, ESA managed to take a mass spectrometer to measure this material, and they found a lot of things, including glycine, which is one of the simplest amino acids. So we have amino acids on rocks flying around space. So, you know, we need to think about how this chemistry came to be and if we could find signatures of things like this in protoplanetary disks. So dust grains, I like to think of them as little astrochemistry powerhouses. They're not perfectly circular. They're probably fluffy, little aggregates of material made of silicate and carbon. And they're surrounded by ice, depending on the temperature. So we have potentially a water-rich ice, have an ice with CO, carbon monoxide. Those are some of our most abundant simple molecules. And depending on the temperature, these molecules will stick to the grain or they'll jump off. So at about 20 Kelvin, we have CO, which is pretty volatile, and below about 150 Kelvin, we have water. So water is going to be on the grains for a much larger proportion of our disk than our CO. And within these dust grain surfaces, we can do chemistry. And this is what Karen does in her lab, where you take ice and you let it get together, and it builds these larger molecules. So methanol is our simplest complex organic molecule. It has carbon, hydrogen, oxygen. And this is kind of the cornerstone of complex organic chemistry. So methanol forms pretty easily in dust grains, on dust grain kind of ices, where we have CO, we add hydrogen to make formaldehyde, we keep going and we make methanol. And this can happen really efficiently, just kind of in the cold, dark conditions of space. With a little bit of energy, maybe some UV photons or cosmic ray, it's shown experimentally that you can build much, much more complexity with very little energy input. So you can build these larger molecules, you can even build glycine. So that's like pretty cool. And all of this can happen just in a molecular cloud in space. So we're not even building planets. We're not even talking about moons or comets. We're talking about little dust grains in space. So these have ice mantles. And what we want to think about is, does the history of the material in the disk matter? Does what's happening here feed all the way through this journey into disks and then into other more evolved bodies? When we look at very young stars, they have a lot of complex molecules around them in the gas phase. So all of these ices get heated up by the baby stars, and all these molecules sublimate, and we can see them with the telescopes. We can detect a whole host of molecules around young stars in the gas. When we look to our solar system, as I've mentioned, there's a lot of complexity. So what I've been trying to do is find this complexity in protoplanetary disks, and try and connect the different threads of this journey. Because we want to know if what happens here matters for here. Do we start from scratch when we form a disk? Is it such a violent, quick process that all of our ices are destroyed? Or do we preserve some of this material all the way through? So the problem is that these molecules are attached to the dust grains a lot, so it's very difficult for us to actually see them in the gas. So with ALMO, we're looking at gas phase molecules. If we want to look at the ices, it's very difficult, and looking for these complex molecules in the ices is really beyond, I think, even what JWST is going to be able to do for disks. So seeing them in the gas is the only way we can observe them. So if we take a disk and maybe a pre-solar analog, young T-Tauri star, we have our star here, it gets colder, the water and comms are frozen at about the same temperatures, 100, 150 Kelvin. So this is happening on about 1 AU scale in disks around lower mass stars. When we think about observations with ALMA, we can only really probe things on tens of AU scales. So most nearby disks, when we're looking at them, most of these molecules are on the ice, and we're not going to be able to see them. And that is a bit of a problem. But what we've been doing is trying to just look at disks around slightly warmer stars. If we have a hotter star, this snow line is going to push outwards, and we can actually see some of these molecules in the gas. So this is pushing to, say, a 2 solar mass star, young star. We can find these complex organics on tens of AU scales. And this is what I've been trying to find. So if I go back to my family of disks, I want to say this has been pretty incremental. I think every year we looked at a new disk and we found these molecules again and again. It's taken a long time to build up this gallery. And we started with this first one on the left. I think I got this data the week the world shut down with the pandemic, and I had stuff to do in quarantine, I guess. And we slowly built up a picture of more of these complex organic molecules in these disks. So now we can show a pretty gallery like this. To me, it's pretty. The blobs have got smaller and smaller over the years, but they're still spatially unresolved. But we have this bright methanol gas. And if you remember the previous images, it looked very similar to the SO molecule, so quite small and compact relative to the resolution that we have. So we've seen that this chemistry seems to be ubiquitous in these types of objects we're looking at. These are some of the biggest disks nearby, around slightly more massive stars than our sun. So they might not be typical solar systems, but they're showing us something we don't get to see in typical solar systems, which is what makes it exciting. So this disk on the right, we just published over the last couple of weeks, and we found a really rich reservoir of complex organics. We found over 13 different lines of this molecule, so we don't look for one molecular line, we look for a lot. We found a lot of lines where we're going from kind of the properties of these lines have upper energy levels of 20 Kelvin to almost 800 Kelvin. So we have such a huge lever in excitation and line properties that we can learn a lot about the molecules in this disk. So what we like to do is just make straight line graphs. So we have 13 transitions. We take their intensity and plot them as a function of the line properties, and we can try and pull out the conditions in the gas. So these are all of our data points. We reject a few of them, so we think these lines are optically thick. And then we fit a straight line, and we can see that the gas has a temperature of about 230 Kelvin. So this is pretty warm. Warm enough, that we are definitely within the water snow line of about 150 Kelvin. And now what I've been trying to do is reach out and stretch out this kind of not statistics, but this understanding to a larger sample so we can see maybe what some of the typical conditions of this reservoir might be. So I can't do this by myself. I have a lot of great people that I work with. So we start with Hannah, who is an undergrad here at Harvard. She did this for her junior thesis. We looked at a different disk. We got a temperature of about 100 Kelvin. Malou is a grad student at the University of Leiden. We got a different disk, about 125 Kelvin. And then Lucy, a postdoc, University of Leeds, we got about 150 Kelvin. So I think we're not at the stage where we can say, why are these temperatures different? But we can say that they're all warm. So we have some consistency there, but we're not at the point where we can understand what these differences are and if they are significant or not. So if we have our little cartoon, all of these disks had large central holes, cavities, maybe due to forming planets. And we see this rich kind of chemistry happening just at the edge of the disk. We have this heated wall of material where we see this complex molecules in the gas phase, and that's great. So we found molecular complexity in disks. That's really great, but we want to understand where it comes from. Can we make these molecules in the disk, or do we have to invoke this inheritance argument that we have to save them from earlier times in star formation? So we went to our little dust grain. We can make methanol in this CO-mediated ice chemistry. The problem is a lot of these disks are warm. And by warm, I mean most of the midplane is higher than 20 Kelvin, which means we don't have this ice. The CO ice that we're going to make the methanol doesn't exist in the systems where we find the methanol. So that's interesting. And that means we really probably have to invoke this argument of inheritance. Our ices need to have some methanol in them when we're starting to form our planetary systems. We have to preserve some of this material because we can't make it in disks. So this is a pretty fun argument to make. I think I believe it. I get excited about it. We're finding these molecules in disks. And this is the best, easiest way to explain that they're there. So in this system that I showed you all these lots and lots of methanol lines, we actually found isotopes of methanol for the first time. So we have 13 methanol and deuterated methanol. It's the first time we found either of these molecules in a evolved protoplanetary disk, and we're finding that they're at abundances of a few percent relative to methanol. And what that means is methanol is giving us the top level of complexity, kind of maybe the mass of kind of our complex reservoir, but we're getting down to a few percent of methanol. So that's really digging deep into the kind of depth of this organic reservoir. So we have these isotopes, which is pretty great, and we can use them to kind of understand this inheritance story a little bit more too. So the 13 carbon that we see is a little higher than it should be in this disk. So this is our point here for our class 2 disk. As we go to younger stages, we see similar values of about 25 to 30 is the abundance ratio between these two isotopes. In the local ISM, this should be around 70. So we see that in young forming stars and protoplanetary disks, we have more heavy carbon than we should. When we look to solar system comets, 67P, we kind of see the opposite. So this is a little bit of a disconnect that we don't truly understand, but I think that the fractionation of carbon is a little more complicated. A cleaner story is when we look at the deuterium. So deuterium is heavy hydrogen. And when we do that, we can see that these purple points are all kind of on the same scale. So the molecules can become enhanced in deuterium at low temperatures when they form. So this kind of supports that this methanol we see in this disk formed at very low temperatures in molecular clouds. It kind of connects these two threads. We can see that the range that is seen in comets here is kind of overlapping with the other stages of star formation. So this is another kind of line of evidence that we're inheriting materials into forming solar systems. Okay, so what we want to think about now is what else is hiding under the surface. We found this first level of molecular complexity, and we want to dig a little bit deeper to see if we can find bigger molecules in disks. So it is possible, we've done it. There's one particularly molecule-rich system, IRIS-48, which has this asymmetric emission pattern where we have a lot of methanol. And then we found methyl formate, which is this molecule here. We've kind of added on another functional group. We have dimethyl ether, which is a 9-atom molecule, which is pretty big for a disk. And then we also found this weird molecule, ethylene oxide. So I'm a physicist. I didn't know this was a molecule until I found it, and I looked up the spectra, and I was like, oh, that's fun. And this is kind of neat because it's a ringed molecule. And this was the first time we found what we're calling a heterocyclic molecule in a disk. So this is a ring where we have 2 carbons and an oxygen. And ringed molecules are pretty fun if we're thinking about prebiotic chemistry. So this is our disk molecule, ethylene oxide. Real chemists might call it epoxide. And this is its little functional or kind of schematic of its structure. This is a 3-member ring. If we build this to be a 5-member ring, we have a molecule called furan. If we add functional groups to this, we have ribose. And this is a pretty important part of RNA. And this has been detected in meteorites. So we find these molecules in disks, and they're there, maybe more abundant than we expect them to be. And maybe there is a path to more complexity that's hidden in the ices that we might not be able to detect, but this gives us kind of a first instinct that it's probably there. So we have a few other large molecules in disks, and the abundances we want to compare to these younger solar systems, right? Our deuterated isotopes, the presence of methanol tells us that we're inheriting these molecules. So maybe the abundances of these other molecules will be similar. This is our dimethyl ether and methyl formate here. So in young protocellular systems, these molecules are there at about the 2% level relative to methanol. And when we're looking at our older class 2 disks, we see it's very, very different. We have an orders of magnitude spread in abundances relative to methanol. This is percentage of methanol in a few different objects for these different molecules. And we can see that in some systems, the abundances are about 1-to-1, the same as the protostars. But in other systems, there's an order of magnitude difference, and it swings like both ways. So there's something going on here that we maybe don't understand. And in that system with all the fun isotopes, we find that it has a similar abundance in some of these molecules. So there is a huge kind of variation we're starting to see as we piece all of these data sets together. So we want to try and understand if this is chemical diversity. So can we explain abundances that look this different, or are we doing something a little bit wrong? So we can test some of this with chemical models. So we think we're going to inherit material, but maybe over the lifetime of the disk, it's going to change a little bit. So what we have here are some kind of 2D slices of disks, where we have as a function of radius and height, the abundance of an ice. So this is methanol ice here on the left, where it's orange, we have a lot of ice. We have the dimethyl ether ice here, and the methyl formate ice here. So what we're going to show now is as a function of time, how the abundances of these ices change. So we see on the left that the methanol ice is disappearing. We're losing it as a function of time. It's getting eaten away, it's getting destroyed, and changed into other things. And some of those other things are these complex molecules. You can see that these build up in abundance in time. Relative to the methanol initial starting abundance, they're still low, but they're growing. And what's interesting is that they grow in different parts of the disk. This dimethyl ether is growing in the colder part of the disk, and the methyl formate in the slightly warmer part of the disk. So maybe some in situ disk chemistry altering our inherited abundances might explain some of the things that we're seeing. So we want to understand how complexity changes over the disk lifetime. And I think now we have some observations to kind of ground our modeling and our theory. We can start to explore this. But I think we have very good evidence that we inherit our ices from earlier stages in star formation, but they do sit in the disk for 1 million years, and we can't expect nothing to happen. So we might, in an optimistic sense, enhance molecular complexity over the lifetime of the disk. And that could be driven by this disk, these molecules, or these ices are going to drift inwards over time. They are in accretion disks. The ices are going to warm up. As they get warmer, the little radicals in the ice can become more mobile, can induce chemistry. But you also have radiation from the central star, UV rays, cosmic rays. So there's a lot of chemistry that can happen in this stage of planet formation. If we just start with the methanol, we know we can build a lot. And this might be what is setting all of the cometary abundances as well. So this is kind of the last little piece in the puzzle. So yeah, this was big question number 2. Are any of these distant exoplanets hospitable to life? I have no idea. But I think that the basic ingredients for prebiotic chemistry are hidden in the midplanes and the ices of protoplanetary disks. So that's something that I think is really fun that we can start exploring now with ALMA. Great. So this is everything I've got for today. I'll go through some takeaways. So planets are forming in very chemically rich environments. So we can look for tens of different molecules in disks where baby planets are forming, and we can map that on tens of AU scales with ALMA. So that's pretty incredible. If we spatially resolve this, I think we can really map the accretion reservoirs of new planets, which is pretty amazing to do. Watching a planet be born is a great feat. So in some of these disks that are warm, we see all these ices that are thermally sublimating at around the water snow line. And this is giving us a window into the full volatile reservoir, in particular the complex organic reservoir in disks, that we don't really get to see in any other way. This is really only possible with ALMA. And we're finding complex organics, building blocks of prebiotic chemistry. They're abundant in the disks, in certain types of disks. And we think that they're probably inherited from earlier stages of star formation. But what's pretty neat is that we're probably processing and changing this material during the course of planet formation. So hopefully we're going to enhance complexity and not get rid of it. But it's pretty good that we can start to investigate these big questions now that we have the data. So yeah, thank you all for listening. Happy to take questions.
Thank you, Alice, and open for questions. Yes, Paul.
Super basic question. Like when you see images like early on in the talk, and it seems to indicate that, you know, this molecule is coming from a different radius, so that, are you really looking at the mass of that material, or is it the emissivity weighted mass and you have to back out the emissivity?
Ideally, we're looking at a particular molecular line which is excited under certain conditions, so we're not sensitive to the total reservoir of a particular molecule. So we have to be a little bit careful. And ideally we do multi-line studies where we look at different temperatures of lines, and typically it seems like they're tracing similar regions, but yeah, that is something we have to be careful of.
Other questions? Yes.
So I was really struck by this observation you were showing where there's the sort of shocked wake of a planet, and I was thinking about the story you're telling us where these molecules fall into maybe the outer disk and they're sort of slowly moving in. How would that chemistry change if they go through maybe a phase where they are briefly heated up by a shock wave or something else?
Yeah, I think it depends on the strength of the shocks. I mean, we think, to me, like a weak shock, maybe we're sublimating water in the ices but not sputtering the grains.
Is that a temperature threshold?
Yeah, I think
Okay.
a temperature thing, I think. But no, it should have an impact. But then the molecules may just equilibrate and freeze out again on certain time scales. But I think coupling chemistry with like physical or hydrodynamical models is tricky. So there's always like a physical timescale versus a chemical timescale. But I'm hoping that people will start trying to do some of this.
Amazing, thanks.
I have a sort of general question. So ALMA has transferred our understanding of protoplanetary disks clearly. What is your view of what will happen in the next 30 to 40 years? Because I don't think there's any like 10 times ALMA on the horizon.
I think there's still a lot we can do with ALMA. Right now we're very kind of bandwidth sensitivity limited, so we're looking at very small regions of the spectrum. ALMA's going to upgrade over the next 5 years to observe much larger simultaneous bandwidth, so that means we can look for a lot more things at once, which is going to help. And I think long term, hopefully they do build more ALMA antenna. But I'm viewing it as a long-term observatory that is going to keep giving, I think.
Any other questions? Yeah, Charlie.
So the slide where you talked about how we get RNA was pretty cool.
Yeah.
Can you?
No.
What are the? How do we actually do that?
It's not. That wouldn't be my talk. But no, yeah, it's pretty fun though to start finding these kind of molecules. I think you can build some of them. I think you can make some of these bigger things in the lab, but right up to RNA.
Well, like maybe to that point, if some of these super complex molecules are coming from early on, is the planet then just like a holding tank for that sort of like more complex like life to come into being, and it's sort of really seeded by the original ices or something?
Yeah, I guess in my story we're being optimistic that cometary impacts will deliver material that isn't totally destroyed. I think you're not going to accrete these materials directly onto a planet. It has to be delivered later. But I think it's still open as to how that's going to happen and how effective it is.
Yeah.
Gary, did you have a question?
Yeah, it's maybe an inside baseball question that probably Karen has told me more than once the answer to. But in your cartoon of ice-covered dust grain, you have water and then you have CO.
Yeah.
And you were looking to make to see if you could make methanol
Yeah.
in that environment. And of course, the outer layer of CO is more volatile, so it will disappear, from which you conclude that the methanol was probably inherited. But if the CO is mixed with the water, you know, that it's not in pure shells,
Yeah.
does that inhibit the sublimation of the CO enough that you might be able to make the methanol in situ?
Yeah, I think like a little bit of entrapment is probably happening. I think it's hard to tell. We can't really trace very well the kind of abundances of ices in the disk. But yeah, a little bit of CO might do a good job, but I don't know how much you would need. I think it would be great if we could have a measure of the methanol to water abundance in the regions of these disks. That might tell us how much methanol we have relative to water, and if that's what we'd maybe expect if things were entrapped, or we actually have a very rich reservoir of methanol from an earlier time. That might help. But yeah, there might be, we don't know the structure of these ices. I showed them as layered, but they might not be, they'd be all mixed in, or it's a bit complicated, but yeah.
Thanks.
Any other questions? I have a question. I'm curious, you showed a variety of different disks, but there was one, I think it was Ophiuchus
Yep.
48, that
Yeah.
looked pretty different. So what's going on in that one?
That's one of the most kind of asymmetric disks to date. So it has a very nice symmetric ring of gas, but all of the large dust is sitting on one side. And it might be in just kind of a vortex induced by a companion interior to the dust. So there might be a large planet or a young star that is kind of cause an instability where all the dust clumps together. But we think that it might be quite turbulent, and maybe that's why we're seeing a lot of complex molecules, because the grains are moving around a lot and coming up and sublimating and recycling. And we see a lot of a lot of molecules we found for the first time in that disk. It's particularly unique.
Okay, last chance for questions? No? Oh, yes? Calling. Oh, okay, now we've got two.
What's so hard about phosphorus? Why is it hard to see? Or?
I mean, we haven't really looked very hard, I would say. We're trying, but yeah, with ALMA we're going to look at various particular windows for molecules, and it's not typically covered. But phosphorus is typically only seen in shocked regions, and we don't see it in the kind of hot gas around young stars, but we are trying to look at disks as well. It just takes time. Yeah.
I read it best.
So I'm wondering if you could say something about how lab experiments could help you in terms of looking at how these processes evolve. And do you think you're at a stage where your measurements could put realistic constraints in the lab?
Yeah. The lab stuff is great. So what we can, in the lab, you can say you take a methanol ice and you warm it up a little bit, and you can see if you build these larger molecules, you can see the impact of like UV rays or X-rays, cosmic rays, energetic particles, to see what levels of complexity you can build. And then ideally we compare the lab abundances to the observed abundances to maybe see what processes are the most important. What is hard to do is when we try and interpret these also with chemical models, where we try and figure out what rates these reactions are going to take place at. That becomes complicated as well. But the lab stuff is great, and well, we think of something that Karen can explore for us. But yeah, having these warmer methanol ices in the disk and seeing how they transform into other molecules is something that I think we should think about.
Okay, if there, yes, there's
Alma question again.
Yeah.
Are you using the maximum resolution of Alma? It looks like a little more spatial resolution might be quite helpful.
Oh, it would be. We're trying. So these molecular lines are not very bright, so we typically have to do some like pilot studies and look at a few systems, find the brightest ones to follow up. So we're trying. We've submitted proposals to do much higher resolution observations on these systems where we find these bright lines, because we want to know where they're coming from, what the shapes are. So yeah, definitely, we'll try.
But you're limited by sensitivity.
We're limited by
rather than the size
sensitivity,
of Alma.
not the size of Alma, no, more sensitivity. But I think we can do it in a few systems.
Okay, if there are no more questions, then I'd like to thank Alice again and then play down.
Thank you.